Recordings rolling. It's Wednesday, October 29. So past couple days, we've been going through all these posters, which pretty much cover every classic example of a energy type physics one question that you can get. Right, so I'm right near the end. It could have used about 5 more minutes yesterday, so gonna show you guys that escape speed. Right, so leave that. Right, then you guys have been holding on to these 3-page tables for a couple days. There's 12 examples, so we'll go through those. Latest week for you guys. I have this pendulum speed lab. So remember, you can, if you know the length of string, the starting angle, you can calculate the speed that this mass can go through the bottom of the pendulum. But you can also take a speed gate. You can measure. So measurement versus calculation. So this always worked out really well in the past. Next week, I'll set you guys up with the pulleys lab so you guys can rig up some of those pulleys, like that one over there. Okay. And then AP Classroom, Unit 3, you guys remember, is due on Monday. Okay. I also got some puzzles from your textbook. Okay, so you guys got brand new textbooks this year. Well, actually, these are honors. These are for AP. Okay. So eventually I'll get these in your hands and we'll be solving some of those too. Okay. Oh, and yeah, top scientist. Yeah, top scientist. Yeah. I was for emotion gravitation. There you go. So come on, then. Awesome job. You made the list. List. Oh, guys. Yeah, I haven't handed these quizzes back yet because, well, right. Everybody in my period 1 class is turned into quizzes, so that's good. But in my period 4, I think there's 6 quizzes I still need. Okay, so yeah, I'm not gonna be behind. So I gotta get all those first. All right, so hop back in. See, where were we leaving off? It was right near the end. All right, so we were right near the end. Let me see. Okay, so you guys do some simple machines. We did simple machines. We moved down. Did all those. Okay. All right. I think this may have been the last one you guys saw yesterday, and then the bell was ringing. I went through it a little bit faster than I meant to. So, okay, this first thing. Okay.
That was so good. That was the beginning.
I hate quizzing.
I was
Okay, so first thing again. You guys remember, for gravitational potential energy, we've been using MGH, right?
Yeah.
Okay. But guys, the catch with MGH, reason it doesn't work all the time is because that lowercase g right there, that gravity field. Well, if you're significantly changing your altitude relative to a planet, then that g could change, couldn't it? Right? No, if it's pretty well constant, like from the top of Mount Everest down to sea level, it doesn't really significantly change, right? So you can just call it, you can still use MGH, okay? But what if you're sending a rocket all the way to the moon? Well, then this kind of falls apart. You need more universal form. Right? I think in this packet, I got an example with like some asteroids gravitating. Yeah, it's the very last example. Has some asteroids gravitating closer together. Okay, so you need more universal form. Here's more universal form. It almost looks like universal gravity force, which was GMM over r squared. Yeah, except that it's just over r. So kind of like a force times distance thing to get to energy, and also it's negative, right? And so why would that be? Well, here, watch how it plays out. I'll just show it by proof, like why this actually does lead to this. Like if you just start from us, right? Okay. So, let's say you go from, say, the top of Mount Everest here down to sea level. And we say, what's the gravitational potential energy? So I'll call it like delta U, right? And I'll play out this one. So we got negative g, and then right, mass of the Earth doesn't change. The mass of whatever your mass doesn't change. Universal gravity constant, right? But this r changes. Right? So we got an r2 versus an r1. Right? So I'm taking the difference in these two fractions. You guys see that? Right? And guys, how do you take the difference of two fractions? You have to get a common what? Denominator. Right? This one's r2. This one's r1. Those are different values. Hey, can I multiply top and bottom by r1 over r1 and r2 over r2? I can do that. Right. And then I can shove it all into one giant fraction. Then I can factor out the GMM, which is the same for both. Okay. And I got a difference of radial sizes. Right. Now, if you organize the different groups of variables here, okay, I'm going to leave that envelope. That's your mass or point mass. Right. Right. Here's universal gravity constant, mass of the Earth, and maybe 2 different radial sizes that. What if they actually are not crazy different? Going from top Mount Everest down to sea level. Right? You guys know if the Earth was the size of a bowling ball, it would actually be smoother than a bowling ball, Mount Everest included. Right? So, in the big scheme of things, right, it's not a huge height difference. Right? So, guys, because R1, R2 basically be R squared if they're not that different from each other. Right? And oh, guys, what is GM over R squared? That's that gravity field right there. That's why I colored it the same. That color is that color. Guess that? Right. Oh, and R2 minus R1, because maybe there is a little bit of difference. Right. Couldn't that just be the height change? So you see that leads to MGH. Is that hey, which is consistent with all the other energy physics we've been doing so far. Okay. I guess good with that. Okay. And you do need this universal form of potential energy to help explain escape speed. And so how's this working? So here, give you guys a picture here. All right, what if you had a big empty universe with nothing in the universe except for two things? Here I'm going to have the Earth. Right, so here's E for the Earth. And then on the complete opposite side of, say, the galaxy or something, right, is a little tiny lab weight right here. It has some mass. Okay? So Earth has some mass, capital M, and maybe some radius R. Okay, and maybe we got this lab weight that's over on the other side of the galaxy. Okay, you guys get that? Okay. And let's say everything's just at rest. Guys, if everything's at rest, then what is the kinetic energy in the system? Zero. So everybody agrees there's zero kinetic energy right now. Everything's just kind of floating around. Okay. Also, guys, look at this distance. Isn't the distance across the galaxy just extremely big? Extremely big. Yeah. Now, if I look at the universal form of gravitation, guys, if you divide by an extremely big number, this whole fraction approaches what? Zero. Yeah, zero. Right? Some students get that. Some students are wait, what? Right. Guys, what if you buy a lottery ticket and you have a 1 in 20 million chance of winning? That means you basically have a what chance of winning? Zero. Right? So 1 over 20 million. This radius like 20 million light years or whatever. Yeah, basically zero. Okay. So that means there's how much potential energy in this system? Zero. Right? Wait a minute. Zero kinetic, zero potential. So how much mechanical energy is in the system, basically? Zero. Yeah, everybody agrees there's zero mechanical energy, right? Which maybe I can kind of address this negative right here, because as maybe it feels like a tiny tug, they start pulling toward each other. Right? Now the Earth is so massive that it moves very little, but maybe this thing, half a kilogram, starts scooting across the galaxy. You guys see that? Because there's a tiny gravitational pull. They start pulling together. You guys see that? Right? Wait a minute. This is now in motion. Now does it have kinetic energy? It does, but you can't create energy from nothing. So is it losing gravitational potential energy at the same time? This extremely large height, like 20,000 light years, whatever it's at, right, is actually getting shorter. Right? It's kind of like it's losing height relative to the Earth. Right? So it's picking up kinetic from potential, but it started with zero. Right? Oh, do you guys see now the potential energy from a universal sense is becoming more and more and more negative? Right. So like if I sort of made a graph, right, you could say like, here, I'm going to make a bar chart. I don't do a ton of bar charts in this class, but AP likes bar charts. So here, just so at least you can see it. Okay. I'm going to do before and after. Okay. So before, okay, how much energy do I have? And I'll do K for kinetic, and I'll do U sub G for gravitational potential. Okay. And I'll do an after. Okay. Maybe after it's been scooting across the galaxy and it's picking up speed, going faster. Maybe it gets to like halfway, like here, something like that. Okay? And I'll say, what's the energy in terms of kinetic and potential? Okay, something like that. Okay? So it starts off with zero in the system. Is that right? It starts off with zero. Okay. But as this object is falling closer, isn't it picking up kinetic? So maybe kinetic does something like this. Right? We'll pick up kinetic. Okay? But the total energy has to zero out, right? So doesn't the potential energy is always negative in this universal context, right? You guys see that? Okay. Because these two bars have to add it to zero because it always started with zero. Okay. That's why this is always negative. Right. And it was consistent with this anyway. Right. Is that okay? Right. Now, basically, this lab weight's falling from the edge of space. Falling from the edge of space. Is it eventually going to crash into the Earth? Yeah, eventually. I mean, Earth's pulling on it, so give enough time, it eventually pow. It's eventually just going to crash into the Earth. How fast is it going to crash into the Earth? Do you think we can solve that? Well,
of course we can.
Yeah. We can solve that. Okay. So actually, the answer is right here. So kinetic plus gravitational starts out 0 joules. Right? It starts off at the edge of the solar system, right? At the edge of the galaxy. Right? Then as it's falling towards the Earth, it's picking up more and more kinetic, and it's losing more and more potential, but it still has to zero out. Hey, can I scoot this over here and say this term is equal to this term? Right, right. And then when this lab weight from the edge of the galaxy finally, pow, smashes into the surface of Earth, isn't the distance from the center of the Earth equal to the radius of the Earth, which is capital R? Right. So you do that. So I can pick up from here. I can say so. Something about 1/2 the mass of the lab weight times its speed that's picking up squared is equal to, and then if I add this over, it becomes positive. It's G M over. Guys, I'm going to change this variable lowercase r to a fixed capital R for the radius of the Earth. Okay, you guys see that? Right. Okay. Now, what I want to know is how fast is it crashing into the surface of Earth? Guys, if it fell from infinitely far away, is it moving infinitely fast? No, turns out no. Right? It has some finite speed, which we're going to solve right here. Right? It fell from the edge of space, right? It fell from the edge of space. Right? What's sort of like the maximum speed that it could crash into Earth, falling from the edge of space? Right? Right. Oh, guys, what cancels out on both sides? The mass of the object itself. Right? Right. So guys, whether I have this object or this object, would these fall together, and then crash into Earth, same speed, same time? Yeah, they sure would. They sure would. Yeah. How about well, can you solve for that B? Right. Maybe we'll call it B crash. Or B crash. Right. B crash. Well, B crash squared would be 2gm over r. So what is B crash? Square root of 2 times the universal gravity constant. Remember von Jolly's number 6.67 times 10 to the negative 11 times the mass of Earth that's put pulling on it for maybe billions of years. But okay. Divided by the radius of Earth, because that's the crash point, right? Right, you guys see where that's coming from?
Yeah.
Right. So if something fell from the edge of space, it would crash that fast, right? If you plug in some numbers and get a numerical scale. Actually, you know what? Here, let's do a little practice just for Here, it's probably good practice just to throw some numbers in. Okay. So I got a 2, I got a 6.67 times 10 to the negative 11 meters squared per kilogram squared. Okay. I got a mass of the Earth, I'll call it 5.98 times 10 to the 24. That's kilograms. Right, you guys have your calculators ready? You know we're about to do this number, right? Right, and then the radius there, 6.38 times 10 to the 6, and that's meters. Right, so make sure this is all grouped up. See if you can correctly plug that into your calculator. Here, I'll do it on video in front of you guys right now. So I'm going to do square root. Now, this calculator does give me one parenthesis. I do have a bunch of stuff grouped together after that, so I'm going to open up multiple parentheses. Guys, as soon as if you only have one parenthesis, as soon as you close that parenthesis, it stops square rooting. But I want everything square rooted. So I'm going to open up an excess of parentheses. Just a little hint here. Okay. 2, 6, 7, 10, negative 11, 5, 9, 8, 10, 24. And then divide by, and then, guys, after you hit divide by, definitely open up another parenthesis because there's that multiply down here. They got to group together. 6, 3, 8, and then 6. Okay. Right. Now, I'm going to make a prediction because I think I should know this number. Teach this class a long time. If something falls from the edge of space, I think the number should be 11,000. I think it's 11,180. I think it's what it is. Meters per second. Right. I think it's what it is. Okay, that's what you guys get into. Let me see if that's exactly what I get. 11,180. Oh, I missed it by 2 meters per second. Oh, yeah, no, same thing. Same thing. Could you call that basically 11.2 kilometers per second? Yeah, that's that, isn't it? Okay. Now, are you guys ready for a different question related to this? What if I'm standing on the surface of Earth and I have this, and I throw it straight up into the sky, and I throw it as hard as I can? How fast would I have to throw it so that it goes all the way to the edge of space?
92 kilometers per second.
Same number, 11.2 kilometers per second. Right? Right? Hey, is that how fast you have to get going to escape the gravitational field of a planet? Is that escape speed? It's the same thing. It's escape speed. Right, so now you guys can derive escape speed. You guys can do that? Right. And you guys see this in terms of format, looks a lot like orbital speed, doesn't it? Guys, what's the difference between this and orbital speed? Just get rid of this 2 here, right? Oh, Hey, that might be a nice shortcut. Guys, if you know what orbital speed is, can you just multiply by the square root of 2? And now that tells you how fast you have to go to escape. Yeah, right. Here, one more thing about escape speed is that you don't actually ever have to be going this fast to escape the speed of the planet as long as you have the rocket engines on. Because if you're in a rocket, you're just going very slowly. Could you go like very, very slowly and still get away from the planet?
Yeah.
As long as the rocket engines are blasting. Yeah, right. But what escape speed really means is like how fast you have to go so you can cut off the engines. You can just coast from inertia. And yeah, the planet's pulling on you, and you slow it down a little bit, but you still have enough speed to get away. Okay. All right. I almost forgot about this one. Guys, you're going to get this as an AP question. This will come up on the AP exam. So, you guys remember how powers work compared to time?
Yeah.
Right. So know that if there's like if you have a 20-watt light bulb, isn't power measured in watts? Right. 20 watts, and you run that for like 60 seconds. Can you multiply 20 watts by 60 seconds? Get how many joules of energy you just pulled off the grid or out of the battery? Right. You can do something like that. Right. Okay. So powers work over time. Okay. Now, here I'm covering this up because I want to see if you guys can figure this out. Drive this. Right. Guys, what does work equal to again? What times what? Force times distance, is that right? Right, and then time I'll just call it t. So that can be okay, right? Is that okay? Right. Now, what if I group these variables together different? I could work backwards. Oh, force distance, that's work, and then just work backwards to start. Right? Or guys, can I group together this distance over time right here? What is that called? Velocity? Force of velocity? Huh. All right, and I gave you guys a picture here. Because again, like almost guaranteed you're going to get this question on the AP exam. You're going to say some version of an elevator is being pulled up at some speed. What was the is? Do you guys think there's a motor at the top of the elevator shaft that's pulling up this elevator? Right. What's the power output of the motor at the top of the shaft? You know, how much is it pulling? How much? What raise pulling electricity off the range? Sort of. Okay. So all it is the tension in the elevator cable times the speed of the elevator. Okay. Is that okay? That's how many watts you have to pull straight up.
Right. 25,030.
Yeah. Now, in this case, guys, do I have this elevator being pulled up at constant velocity? Is this going constant velocity? Yes. How do you know? Exactly, because equilibrium, because the tension up is as much as the weight down. Yeah. Right. Now, guys, what if you pulled with even a greater tension? This force would go up for greater tension, right? Right. But if you do that, then wouldn't the elevator also be accelerating? So this velocity would no longer be constant. So the power rating would always be changing. So they could ask for like a single instant. They could say like at the 3-second mark, how much power is okay, something like that. Okay. All right. Yeah. So look for that type of question. All right. You guys ready for energy table? Energy table. Yeah. And a lot of these you guys have seen over the past couple of days. So see how you guys did. Okay. So I gave you guys a bunch of scenarios, 12 different scenarios, 4, 4, and 4. Okay. And I have a table set up for sort of a universal set of questions. What objects are in the closed system? If it is closed system, now we have a couple of open systems, but those are kind of the exception. Most of them are closed systems. So what objects are we considering? Okay. But that could be an AP question. If you could just straight up ask you what's in the closed system, and that could just be the question. What's the energy at point A? What's the energy at point B? Right, like guys, a bunch of these questions have been going through over the past couple of days. Right, here, I'll just do one randomly. Boom, like right here, I just opened up randomly. Okay, got energy at point A, got energy at point B. Closed system, they equate. Boom, you can solve the stuff. You guys see that? And then the universal question I have here is, what is the speed of point B? Now that might not always be the ideal question, but here, I guess it is for this table. All right, so let's do it. All right, first of all, oh, Galileo drops the ball from the leaning tower. Oh. No, if he drops the ball, first of all, what's in the system? The what and the what? The ball and also the Earth. Yeah. Okay. So I'll call that the ball Earth system. Okay. Because see, if you did not include the Earth, then that gravitational force would be external to the system that consists of only the ball. Okay. But if I include the Earth, then that gravitational pull is now internalized. Okay. Okay. All right. So what type of energy at point A? Potential energy. And what's the expression for that? Yeah, MGH. Okay. You guys do know that pretty much this whole table we could fill up with just this table, right? Right. You guys just pulling terms off this table. Okay. Which is hanging from a ceiling, I think right there. Guys, is it that one? Am I pointing to the right one?
Yeah.
It's that one, right?
Yeah.
Right here. Yes, yeah. Same thing. Okay. Okay. Guys, this is your equation bank for pretty much this whole table. Okay. All right. So, what kind of? Oh, and you're not allowed to. Okay. Depending on how AP asks a question, you're not allowed to sort of have any MGH if you do not include the Earth in the system. If they say a system that consists of only the ball, then you are allowed to have kinetic, but this MGH they wouldn't really be relevant. And it's just a thing I've seen before. And what type of energy? Right, I guess it's about to hit the ground. Yeah, it's all kinetic. Measures exactly 1/2 mv squared. And that would be at point B. So I'm going to throw a B on there. Now, can you solve for the speed at point B? And I'll do this on paper just so it shows up better on the video. So we're doing sum of energy at point A equals sum of energy at point B. Right. So I got MGH at the top becomes 1/2 mv squared at the bottom. Okay. And the question is, what is the speed at the bottom? Okay. So can you guys solve that? Here, see if you guys can stay a step ahead of me.
Oh, math cancels out.
Yeah, sure does. Sure does. All right, so then say if you cross multiply those two, and VB squared is 2GH, and speed at the bottom is square root 2GH.
I'm so poor. I can do it.
So, right, so you guys write that either in your notes or, well, I guess if you're writing like size 5 font, you could maybe squeeze it in this square. That's okay, great. But yeah, then you guys have the whole process somewhere, right? You guys have the whole process. Right? Guys, it is important to be writing. Yeah, I see you guys writing. That's good. Right? It helps your brain learn the stuff to actually like write it down. Right, so I'm gonna do ... to skip it. Velocity at point B is 3 2gh. Okay. Here, let's do a bonus question on Galileo. What if he throws the ball? Galileo throws the ball. Right. But same question. Right. What is crash speed? Okay, so same question, but a little bit different scenario. Let's do sum of energy initial equals sum of energy final. Okay. Guys, what kind of energy initial? Yeah, kinetic and potential. Yeah. So yes, it has some MGH because he's still at the top of the tower. But he's also throwing it, so it's 1/2 mv throw squared. And that becomes 1/2 mv crash squared. Okay, you guys get that? We're solving for v crash. Okay, is that okay? Now, guys, before we go chugging through a bunch of algebra here, wait, does it matter whether he throws the ball up, down, or to the side?
No.
How many guys think it matters if he throws it down versus up versus to the side versus at like 38 degrees? How many guys think that matters? Turns out it doesn't. Okay. Which I can see why you maybe think it would. Because guys, the old way is solving this. The old way. You guys remember back in projectile days? Guys, what if he throws it at like a 38-degree angle to watch out, or something like that? Wouldn't we have to break this into components and say, well, okay, it's kind of going across and it's kind of going up and then it comes back down and there's so much time and and that would take like several sheets of paper, right? Isn't that? Okay. This cuts through all that. Right? Turns out the crash speed actually doesn't matter which direction he throws the ball at all. Right? This is all in terms of scalars. We can just cut straight through vectors. We're not going to solve for how much time it takes. We don't know where the ball lands exactly necessarily. Right? But you do know the crash speed regardless. Right? Because you just solve it this way. And if you solve it with projectiles, you would always get the same answer. Yeah. Right? So mass log this way times 2. Here, a little bit. So v crash squared equals, okay. So if I multiply everything by 2, I gotta, well, this times 2 would just be v throw squared. Okay. And then I got plus a 2gh. Okay, is that true? And I got one more algebra step, which is to do what? Yeah, square root. Right. Yeah, so v throw squared plus 2gh. Yeah, that is. Yeah, you do remember this from yesterday. How many of you guys remember this from yesterday? I asked you the same question. Yeah, I asked you guys, is the crash speed equal to the throw speed plus root 2gh or the square root of throw speed squared plus 2gh? And you guys told me it was this one. And it is. I just want to see that. Alright, you guys ready for the cannon? It's cannon time. Cannon fires a cannonball at some angle. I didn't even specify what angle. That's interesting, right?
Does it matter though?
Does it even matter? Right. Well, yeah, if we were selling this with projectiles, that'd be the first thing I would do is say, okay, well, I have to know the angle because I have to break it into components, and then I can do my analysis from there. Right? But here, we're going to cut straight through a bunch of stuff, and we'll just solve this all in terms of energy. So here, I'll show you guys how to do it. Guys, what is cannonball? Yeah, that's it. Cannonball, or that's all we're going to consider. Right. Now, if you're thinking, wait, why wouldn't you include the cannon? Right. You would if you included the cannon blast, but we're not in this case. In this case, point A is after the cannonball has already left the cannon barrel, so the cannon blast is in the path. Okay. Right, so all I care about is cannonball, or that's my closed system. Right? And what if the if point A is basically ground level, then what type of energy at point A? Yeah, it's all kinetic, all 1/2 mv squared. Maybe it's tiny until it's basically negligible. Okay. And then I wrote out some arbitrary height. Now, I don't know what height this is. Maybe it goes to the height of the parabola, or maybe not. Maybe it's just like, how fast is it going when it goes up, like 10 meters or whatever. Okay. So what kind of energy at point B? It definitely has some MGH, but it also has some 1/2 mv squared too, right? And that's at point B, right? Is that true? Because it both have a height, but it's also still in motion, so it has both of those. So let's solve for this speed B right here. So here, sum of energy at point A equals sum of energy at point B. Yeah. So like 1/2 mva squared equals mgh plus 1/2 mvb squared. Okay. Let's stop this. Okay. Oh, it looks like the mouse of cannonball. Right here. Okay. And then okay, no. Ooh, this time subtracting over the gh. So 1/2 vb squared equals 1/2 a squared minus gh. Ooh. What we did where Galileo was throwing the ball ended up sort of like downwards. It had to add, right? But here I'm blasting the cannonball kind of upish, so hey, it will subtract, won't it? It's slowing down as it's moving upward. Can you guys times 2 in the square root? So times 2 square root. So I know it's going to end on the square root. And if I multiply it by 2, then this would be VA squared minus 2GH. And that's the answer. VB equals VA squared minus 2GH. Square root of that. Okay. That's good. All right, you guys good? Is that good? Yeah, good. Yes. Okay. Next 2 rows are my 2 open system examples. These are the only 2 open systems I have. Now, open system, you guys remember, usually there's friction that's taking energy out of the system. Right? So let's have an open system consisting of, I'm going to treat the kid in the sled as like one object. His kid's just sitting on a sled. This kid's sledding down maybe like a snowy hill. Right? Let's also throw in the earth. Yeah. Okay. It's still an open system because there's friction. Okay, because there's friction. Okay. So what type of energy at the top? Yeah, definitely there's MGH, right? Now if he starts from rest, then that's all you have. If he gives himself a push, then you could add 1/2 mv squared. I guess it depends how you interpret it. But usually AP spells out its own block paragraph, and they have lots of details. Okay. Okay, so a little bit of interpretation here. Guys, by the time he gets to the bottom, he has what kind of energy? Kinetic, 1/2 mv squared. Right. I mean, he's probably in motion. That's true. Right. Maybe he's not moving as fast as he would had there been no friction, but he has some speed. Right? But he has no height, so he has no more mgh. Right? Now, this bubble in the middle, I'm going to subtract off the work done by friction. You guys, the work done by friction, could that be what times what? What work is what times what? Yeah, force times distance, right? Okay. And what force are we talking about? The friction force. So it's the friction force times, and what distance are we talking about? What distance does the friction act over? L. Ah, it is L. You guys see that L right there? Right. But I've seen AP ask pretty much that question before. Is it something like as multiple choice to say, is it the normal force times the height? Is it the friction force times the length? And that's what it would be. Okay. Alright, so we're gonna set up sum of energy at point A minus the work done by friction results in sum of energy at point B. Okay, so that's an open system right there. Okay. So at point A, I'll just call it mgh, and then subtract off the friction force times the length, and that results in some kind of 1/2 mv squared, where we're solving for what is the speed of the bottom. Okay, before I go chugging with more algebra, guys, could you, if you wanted to, could you do some substitutions with this friction and say, guys, friction force is equal to what times what? Coefficient of friction times the normal force. Guys know that? Furthermore, if you knew this angle of this incline, the normal force is equal to what times what? Mg cosine theta. You guys remember that? All right. Okay. So if I gave you more details, you could do some more substitutions, but I'm just gonna leave this like this. All right. So say I got a oh, actually, it could be helpful if I wanted to cancel out the sim. I bet if this kid has a friend next to him that's like, they're all different sizes, I bet they'd sort of slide down together. Maybe, I think. Let's see, times 2 divided by m square root. Okay, so we gotta do all those things. So I'll do times 2 first. So mv squared equals 2 mgh minus 2 friction force length. Okay. Then divide by m. So that, and then finally you take the square root. B equals to the big old square root. So, okay. I'm sure I'm seeing these square root 2GHs show up all over the place. Huh, that's interesting thought. Okay. I guess if you see that, you have a big old square root and you have a 2GH in there for energy, you're probably on the right track. It might be a good sign. Probably that. Okay. Equals square root GH. Okay. And of course, if they gave you some numbers, you could plug in some numbers. Right? The kid has this mass, and the hill is this height, and this length is whatever, and the angle is whatever. Okay, sure, absolutely. All right, that's it. Right. Oh, car brakes to a stop. Yeah, I have a whole poster just for this one. Spend some time with it. Okay, so actually, I'm just going to include one object in the system. What do you think? Yeah, just the car. Because that's normally how AP would phrase it. They say a system consisting of only the car, right? And at the beginning, the car has what type of energy? Kinetic. Yeah, kinetic. 1/2 mv squared. When the car comes or gets to point B and it's at a stop, what kind of mechanical energy? It has no speed. It has no kinetic. I don't see it going up any hills. It doesn't have any potential. It's nothing. 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 Nothing's what matter. Nothing. Zero joules. Yeah, 0 joules. Wait a minute. Where'd all the energy go? Friction with the road. Friction between the tires and the road. Right. So I thought if you had a thermometer and you measured the temperature of the road, do you think the temperature of the road would go up a little bit? Yeah, okay, but we're not going to quantify the temperature in this spot. Right, so minus work done by friction. Would that be friction force times stopping distance? Like that? Right. Now, who can tell me what goes in this box right here?
0.
Oh yeah. The questions, the universal question there is what's the speed of point B? Okay. Yeah, you guys do see 0, right? Because I'm digging through my posters. Here we go. Okay. Because that's normally not the question that's asked. Normally the question that's asked has to do with what's the braking distance. And that answer is right here. Okay. Right, so you guys see?
There are no numbers then.
That's a lot of that.
There are no numbers.
They're not here.
There are 2 numbers.
H2. Ooh. Actually, I have a poster that looks a lot like this one, don't I? With the block and spring, you let go, it flies around. Like that. So, what do you want to put in this system?
The block.
The block,
Spring.
the spring,
And earth.
and the earth. Yeah. Okay. Because we're focusing on the blocks, we have to include the blocks. Do you guys think if you had a block with a different mass, you'd have a different outcome? Yeah. In this case, you would, because whenever there's a spring involved, guys, if I put this one on the spring, and I let go, it flies around. If I put this one, it's my turn. Might not even make it up there. Right? We have that. So we gotta include block. We gotta include the spring because there's energy stored in the spring, and we have to include the earth specifically because there's a height change. Like the car breaking to a stop, I didn't include the earth, but if we wanted up a hill, I would. So what type of energy at point A? Yeah, 1/2 kx squared. All the energy is in the spring. Okay. So if I told you the spring had a spring constant of like 1,000 Newton per meter, and you squashed it by like 9 centimeters, could you calculate how many joules were in that system?
Yeah.
Actually, here I'll do it real fast. Well, it's 1/2 times 1,000 times and then 0.09 because it had to be a meter, and I have to square that. That'd be like 4 joules. 4 joules. So now there's 4 joules in the system, and it'll go. Phew. Okay. So like that. Guys, what type of energy at point B? Kinetic and potential. Yeah. If they lift at some height, so better have some MGH. But also, it's got to have some speed, and I know that for sure because the only way for it to get there is it had to have gone around this vertical loop first. So there's no way for it to not have some kind of speed and therefore kinetic energy. Okay, so point D. Okay. So algebra time. Let's do some algebra. So sum of energy at point A equals sum of energy at point B. So we got our 1/2 kx squared, which if I throw in some numbers, maybe you get something like 4 joules or something. So we have that much energy to go around. And then some of that energy goes to lifting at this height change. Right? If it's not enough energy, it might not even make it up there. But if it is plenty of energy, then there'll be some left over for it to be in motion. Like that. Over here. Okay, so I think I subtract this over. Got multiply by 2 and divide by mass. Because I did 2 steps from here to here. I multiplied both sides by 2, and I also divided both sides by the mass. Okay. And on the right side, I had to do that to each term. Okay, so the 1/2 disappeared here, and then divide by mass, and a 2 popped up here, and then divide by mass. Right. And last step is square root. And this whole expression is under a root.
2G, they just keep following.
Yeah, there you go. There you go. Yeah. Big old square root. Kx squared on m minus 2gh. That's all in that radical. So you gotta figure out some stuff here. Guys, what if you ran 2 identical scenarios except for, and I'll just change one thing at a time. What if you had a stiffer spring? Guys, if you have a stiffer spring, what happens to the speed? Yeah, it'd be going faster. You guys see if the K increases, the speed's gonna increase. Okay. Now it's not a straightforward relationship. Like if I triple the spring constant, it's like, well, it's kind of ambiguous because it depends on some other things like height changes. How about guys, what if I use a more massive block? What if I have this compared to this and I increase the mass? What happens to the speed? Yeah, it does have to decrease, right? More mass, that would be smaller speed. How about guys, what if I increase this height? Increase this height, what happens to the speed? Yeah, it would also slow down because see you're subtracting. Right. What if I change planets and I turn up the gravity field? Somebody just turned up the gravity. Yeah, it would also slow down. You get these relationships like this? Right, you guys can read the music of these equations. Oh, bungee jumper time! Bungee jumper! I have a poster for this one too. You can figure this one out. So he dives off a platform and barely touches the ground before the cord retracts. Now, point A is at the top of the platform, and point B is just when he's reached down and just touches the sidewalk. He's about to turn around. So once you go into the system,
My crap.
how about the bungee jumper with some mass, and also also the bungee cord. Yeah, because we're gonna treat that as a spring. Okay. And also the Earth. Because there's a height change and Earth's gravity pull is it has a weight. There's gravity force.
Jumper.
Yeah, so all those. Yeah, bungee jumper, the bungee cord, and the Earth. Okay. Guys, what kind of energy at point A? Yeah, there's definitely potential. There's definitely some MGH. Okay. And is there kinetic? Well, it depends how you interpret it. Because now if he just steps off and drops from rest, then there would only be MGH, right? Because what if he does a running jump, like and then jumps off? Yeah, then he would also have the one that we squared. It kind of depends how you interpret it. Okay. I wrote the word dive, so okay, I'll do it. Okay.
How come they the third eye? Wait, never mind.
Yeah.
The one that's right here.
Guys, by the time he gets to point B, where did the energy go?
I have no idea. Wait, no. The spring.
It's in the spring. It's in the bungee cord, isn't it? And that 1/2 kx squared. Right. Okay, is that okay? Okay. Because he's basically at zero height, so he has no more MGH. He's stretched the spring, the cord as long as it'll go. He's about to be retracted, so he has no speed. Right. Yeah. But the fact that the cord is stretched, that's where all the energy went. Of course, it's about to boing go the other way, and it's gonna kind of oscillate back and forth for a while.
He has no PB.
Guys, what does this X represent? The distance of what?
That after it stretches.
Yeah, how much the cord was stretched in addition to its original length. Right, you guys remember that? Right. So maybe the cord has length L and it stretched some additional amount X, and L plus X adds up to this height. Okay. Guys, what's the speed of point B?
0.
0. Okay. Alright, that right?
Got OJ. OJ. Oh no, wait.
Oh, right.
Ooh, I got a couple of that ones. Alright, so I got a modified and I got the classic.
Okay.
So what do you want to include in the system here?
No, but Atwood and elevator at the same time. What?
For this Atwood, what's in the system?
One,
M1,
2,
M2,
the Earth.
and the Earth. Yeah, that's it. M1 and 2 Earth. That's all that matters. You don't have to include the string, it's in terms of the system. You don't have to include this table surface because the upward force doesn't actually do any work because it's canceled out by it doesn't
My precious.
move it upward. Right, so what type of energy at point A? Yeah. Right. Okay. Right, and I didn't really spell out what's going on, but you could probably predict that maybe you start from rest, you just let it go, and it kind of moves from point A to point B like this, that kind of motion. And at point B, maybe this one's just above the floor, like a couple of millimeters, so it's about still in motion. Yeah. So potential energy. But guys, what subscript goes on this M? Yeah, there better be an M2GH. Right. Now, if he said plus M1GH, I mean, I guess you kind of could, but that M1GH would also show up at point B, so we cancel out anyway. Okay. But it's definitely important you have an M2GH. Yeah, because M2 is the one that's actually falling. Okay. That's one that actually undergoes a height change. So you definitely have to consider that. Okay. By the time you get to point B, what kind of energy? Kinetic? 1/2 mv squared? And actually, guys, do both these blocks have the same speed?
Yeah.
Yeah. Right. Does the direction matter? Does it matter that one's going down, one's going to the side?
Oh.
Right. Not for an energy setup, because energy is is a scalar quantity. Remember, we were thinking about that before with the I think with this but we're thinking about that before. So plus another 1/2 mv squared. Now this is mass 1 and this is mass 2, something like that. What's the speed at point B? Do you see the big picture question that we're answering here? Is what is the speed as the result of a height change? Right? Notice I never asked any question about what's the acceleration of the system. We don't even have to solve for that to get to here. Right? I never mentioned how much time it passed. Right? Because if you were ever asked this question, you're given some kind of Atwood, either this one or the next one, saying, what's the speed after some height change? Could you solve it the old way with Newton's second law and then go over kinematic and solve it that way? You could. Right? Or you could solve it this way, which is probably faster for this particular question. So let's do sum of energy at point A is sum of energy at point B. Okay. At point A, I got M2GH. So the fact that this M2 can fall. And by the time you get to point B, now that both these blocks are in motion, M2 is as low as it can go, it has no potential energy, and M1 up here, well, never changes height, so I never even think about any MGH. Right, so it goes to 1/2 M1V squared plus 1/2 M2V squared. Okay. We're solving this V. Hey, could you, if you want to, could you factor out the V squared and here, I'll do it. M2GH equals, so you got 1/2. Could you think about the mass as being like a giant mass block like this? I mean, algebraically it works. Yeah. Okay. And then see times 2 divided by masses. So V squared equals 2. Think of this something like that. Okay. And last step, take square root. It's like that. Okay. So the speed at the bottom is big ol' square root M2 M2G8 over sum of masses. Okay. And this is again consistent with the lab that you guys did a few weeks back. Okay. You guys see the heavier the falling block, the faster it'll move. But the more massive the block on top, that just slows it down because of inertia, doesn't it? Like if M1's really massive, if M1's really massive, wouldn't that kind of slow down the system? Just your dividing, like I said. Okay, guys good? All right. Well, that's gonna be our last point today. You guys have a good day.